Hello navigators, today we are going to talk about adjoint solvers. So you might wonder about adjoint solver, then this is one of the applications of the CFD method. We perform CFD to find out about the flow around some particular object, how the flow is going around this particular object, right? But sometimes we may want to find a shape which is aerodynamic. You might say that the shape should be aerodynamic. That means it should give you some lift or thrust that you want. You have some objective and your design that you're creating must follow that objective. But in order to do so, you might have to do CFD analysis for your changing design. That is not computationally effective. Also, money-wise, it's not very economical. You might want a method for which you can find out that what you should change. Let's say you have something like this, then do you want to do something like this and then lower the curve or keep the curve same? There should be a method which can tell you that what you should do. You should not change it and then find out that it made your design worse. For this, the curve you can parameterize using some parameter alpha, and then you can change this alpha according to what the flow is suggesting you. Those kind of methods which are used to optimize your objective function are called adjoint methods. Let's deep dive into the theory of adjoint solvers in CFD. For example, there is a objective function. Let's say this is J is lift that your object should produce, and it should be subjected to these equations which are the PDEs that it satisfies. These are basically the Navier-Stokes equation. This could be an incompressible Navier-Stokes equation or compressible as well, depending upon your use case. Then, in order to optimize this, to maximize this instead of minimizing, you want to maximize this, or you can also do minimization of the drag subject to this condition that it should always satisfy the Navier-Stokes equation. Then we can use this adjoint method to find this particular alpha. What should be this alpha? In order to find the minimization or maximization, the extreme values of J, you have to find the total derivative of this J with respect to alpha. You'll have to do this, which is the derivative of J with respect to U, then derivative of U with respect to alpha, similarly derivative of J with respect to B, and then derivative of B with respect to alpha plus 2J alpha. So this is what we may have to do. These particular values that we have to find out are called the sensitivity of U and P with respect to alpha. That means we have to solve for this equation, as well as this equation. There are three equations that we have to solve. These equations are called the primal equations, and this equation is called the adjoint equation. And once we have this, we can iteratively change the value of alpha, and then depending upon that alpha, this will also change, and then we have to again solve and then find all these values. This particular process goes on iteratively. We can assign some variables to these values. For example, let's say we assign this as lambda and this as pi. This particular method is called direct method. This is our equation that we want to satisfy, and these values we can assign some other variables. Let's solve them simultaneously. But there is another method which is called the Lagrange multiplier method. In that method, we can enforce this particular constraint in this J, and we can write that as L is equal to J plus some Lagrange multiplier which is lambda transpose, which contains the adjoint variables, and which is this is the constant for the entire volume. This is a new Lagrangian, and for this we can find the sensitivity. This is another method, but ultimately we will get the same equations that we get from the direct method. This is the derivative. If we find the total derivative of that Lagrangian, we'll get these. Here, these two equations, if we satisfy them to be equal to 0, this one and this one, then these are called the adjoint equations. This particular total derivative will be simplified to this. And for this, we have to just find the derivative of alpha with respect to the constraint and this. For just one design variable, it does not matter if you use the direct method or the adjoint method. Once we have this total derivative, we can evolve this alpha, and there are various advanced methods to make sure that this does not have a lot of disturbances, and we find the global minima. So they are conjugate gradient and then BFGS. This has much faster rate of convergence, but it takes a lot of time to perform one iteration. Basically, it estimates this beta, which is the learning rate. Let's now talk about how we can apply this particular adjoint method for incompressible Navier-Stokes equation. So this is the incompressible Navier-Stokes equation, where this is a term similar to the Darcy equation, and this is called the momentum. This is basically the velocity. This particular equation helps in optimizing the topology of the flow. For example, you have one inlet here, and this one outlet here, and one outlet here, and you have this entire box, and this alpha is equal to 0. That means the flow can go anywhere, but ultimately this alpha, as it evolves, it makes it something like this, where alpha is equal to 0, where flow is allowed, and this is alpha equal to 1 and alpha equal to 1. The alpha values are evolved with time in these zones, so that we get alpha equal to 1 in these zones, and we get a structure something like this. This particular method is used in topology optimization. Now, if we construct a Lagrangian for this, which is nothing but our sensitivity, which we are assuming that this particular objective function is just the inflow and the outflow. Therefore, the derivative of the objective function with respect to the flow variables, U and P, these should be equal to 0 for this sensitivity, but it can be non-zero as well. This is meant for this kind of flow only, but if this is left and right, then they matter. Keeping that in mind, we introduce this particular Lagrangian, which is our objective function plus the dot product with these two adjoint variables, and these are the constants. This is the momentum equation, and this is the conjugate equation. In order to solve this, we'll use integration by parts. When we do the integration by parts, let's say we do it for this term, so integration of lambda dot grad p. When we do the integration by parts, we'll integrate this term and differentiate this. We'll get p dot grad lambda plus the integration of this, which is lambda dot something like this at the boundary. For this, there will be a normal as well at the boundary. For this, we can have some boundary conditions so that this term is equal to 0. We can say that lambda is equal to 0 at the boundary. Using these similar kind of boundary conditions, we can have all the boundary terms to be equal to 0. And we move the derivative from the primal variable to the adjoint variable, and we get these equations, which are the adjoint equations. These two are 0, the derivative of the objective function with respect to the flow variables, U and P. Now, our sensitivity is converted to this, where this is our primary variable and this is our adjoint variable. This is just a simple dot product of the primary and adjoint variable, and this is the derivative of this objective function with respect to alpha. These are easy to evaluate. And if this alpha is dependent upon some other design variable, then we have this, which is something which is a little bit advanced, but if there is something, then you can always evaluate this. In order to stabilize the evolution of alpha, you may sometimes have this and there could be a jump or something like a non-zero alpha here, and alpha equals 0 and alpha equals 1 at some other place. So there will be a discontinuity, and that can deteriorate your solution. And you can have checkerboard pattern as well. In those cases, we can have a Laplacian smoothing to your alpha evolution, which will help you to make this topology optimization smoother. These boundaries will be much smoother, and there won't be any zigzag pattern or disturbances. These are the optimization loop that one should follow. First, solve the primal equation, so you get the velocity and pressure at each and every point of the flow. Then you solve the adjoint variable, which are the adjoint velocity and adjoint pressure, and then you find the gradient, and then you update the alpha. For the gradient, you need lambda dot u. For that, you have to solve these two, and then dou j by dou alpha you calculate separately, and then you choose any scheme and update alpha, and then do this until you reach convergence. That this alpha is not changing at all after that. Up to this, we discussed that how we can use adjoint method to solve any flow. But here you might think that if we have some j, which is a function of alpha and b, why do we introduce this adjoint variable? We can directly just say that they are du by d alpha. Let's go back. So you can have these as is here. Why do we introduce these at all? We can just say that this is grad u with respect to alpha, grad b with respect to alpha. You can have these two terms individually defined, and there is no need to introduce these as separate equations. In order to explain this, we'll assume that what if the design variables are 2, not 1? In that case, what will happen? When we have 2 design variables, then how the direct method will look like. These are the 2 design parameters, alpha 1 and alpha 2, and both are Bergman type of design variables. And now let's introduce a objective function, which is just a function of this u and p, and they are not affected by alpha. This will be equal to 0. No explicit dependence on alpha. We can say that when you find the derivative of j with respect to alpha, there won't be dou j by dou alpha. Just this sensitivity will be due to the dot product of the adjoint variable and the primal variables. In that case, when you solve this, you differentiate this with respect to alpha, then you will find this equation. This equation contains dou u by dou alpha 1 and dou u by dou alpha 2. This is one equation, and in another equation you will have dou u by dou alpha 2. There will be 2 equations. And when you want to find out the total derivative of j with respect to alpha, you will have to have these two, which is j by dou u I, and this I will be for both the alpha 1 and alpha 2. You have to have 2 equations here and then get them added here. If we want to compute that how many number of solves you have to do one primal solution of the PD and one sensitivity solution per design variable, alpha 1 and alpha 2. That means you will have 1 plus 2. That means total 3. For n equal to 2, total 3 solves you have to do. This n will increase. Let's say you have 10 design variables. Then in that case, this will be 11 solves. Right. Now let's see if we use the adjoint method. In the adjoint method, we can write this Lagrangian as j plus this. These are the adjoint variables. Basically, we have multiplied this Lagrangian lambda transpose, which is lambda and phi. So therefore, you get these two, and these are the constraints. Now, using that, you'll have these two conditions such that after the inner product, you switch the derivatives. These are the two conditions. If you satisfy these two conditions, then you'll get your derivative of j with respect to u and p after solving these. These are the adjoint equations as we discussed previously. These you have to solve simultaneously. This will consist of one solve for this. Here you can see that both alpha 1 and alpha 2 both are there in this equation, in this adjoint equation, and in the primal equation you already know both are there. So once you have solved the adjoint equation, you just have to find the dot product of these two, which is the adjoint variable and the primal variable. Similarly, for dou j by dou alpha 1 and alpha 2, you just have to multiply with the adjoint variable and the primal variable. Therefore, the number of solves are one primal VD solve as previously, but only one adjoint VD solve independent of the number of design variables. Therefore, you just need two iterative solutions, first this and that, and then it will be independent of the number of design variables. Therefore, adjoint method is preferred when you want to perform any topology optimization or shape optimization in your CFD simulation. This is the comparison for direct and adjoint method. And this is the contrary remark that adjoint method is far more efficient for when you have more than one design variables. And this is the default method. It doesn't matter even if there is one variable, you can always use the adjoint method. But the computation cost will be same. Then the gradient for all alpha is obtained from a single adjoint solve, as you have seen here. Once you have these two, then these two are helping you to get to these. So therefore, just one adjoint solve is helping you to get the solution for the adjoint method. You can extend this to nonlinear PDs. And then this last one is something related to the implementation, which we don't have to worry for now. So in the adjoint equation, we have this term, which are the convective term. This convective term requires special attention. In OpenFOAM, you have to define how you want to discretize these when you are writing the scheme for the adjoint method. These are called the ATC models. We'll briefly talk about them. And while writing the scheme also, we have to write the divergence term for these as negative of rho times u instead of rho times u or rho times some other parameter, like in primal. These are some of the differences that you will notice in the OpenFOAM implementation. Boundary conditions are also a little bit different, which are defined in the adjoint source code that we'll go through when we set up the shape optimization or topology optimization using the adjoint solver that is present in OpenFOAM. With this, we'll stop here. See you in the next lecture. Thanks for watching, and if you like the content of our channel, then please like, comment, share, and subscribe.